Hi there, and welcome to the next lecture. So in this class we're going to be looking at chapter 9, linear momentum and collisions. What we're going to do is start by defining linear momentum, impulse, and what a collision is. And we're going to distinguish between two different types of collisions, both elastic and inelastic collisions. Then we're going to go on to obtain a relationship between the resultant force on an object and the rate of change of linear momentum. And we're also going to use the conservation of momentum to solve problems. And of course, as with all the chapters, we're going to be applying these concepts to solving a variety of different problems. So we start then with the definition of linear momentum. For a particle with mass m and velocity v, the momentum is simply the product between the mass and the velocity. You will recall that velocity is a vector, and for this reason momentum is also a vector. Right, so let's have a look at the first problem then. Your physical education teacher throws you a baseball at a certain speed and you catch it. The teacher is next going to throw you a medicine ball whose mass is 10 times the mass of the baseball. You are given the following choices. You can have the medicine ball thrown with A, the same speed as the baseball, B, the same momentum, C, the same kinetic energy. Rank these choices from easiest to hardest to catch. Right, so what the question's referring to, it's referring to you've been thrown a ball, and there are two different types of balls. So the one option is, or the first ball is a baseball, which is a relatively small light ball, perhaps somewhere similar to a cricket ball. And the other option is a medicine ball, which is a much larger, heavier ball. For those of you who've seen the movie Dodgeball, these are medicine balls that they throw at each other. So the medicine ball's larger and heavier than the baseball. And what we asked to do in the question is to rank three different cases, A, B, and C, and to rank them in order of from easiest to catch to hardest to catch. So what I've done is I've begun by summarizing the information that we've been given. In the question, it refers to a medicine ball, so we're going to use subscript MB to represent a medicine ball. We also, told about a baseball, and we're going to use subscript BB for that. Of course, the medicine ball has mass much greater than that of the baseball. In fact, the question tells us that the medicine ball has mass 10 times greater than that of the baseball. So one way for us to express that or to write that is as a ratio, as shown here. The mass of the baseball over the mass of the medicine ball is going to be the ratio 1/10. It's interesting for us to think about, we've been asked to rank the options from easiest to hardest to catch. So it's important for us to think about, what does it mean if something's easy to catch, or what does it mean if something's harder to catch? And this has got to do with the speed of the object. As I've noted here, the higher the speed, the harder it is to catch a ball. And this has got to do with your reaction time. If balls come into you very quickly, you have a very short reaction time to get your hands in position and be able to catch it. So what we need to do in the question is, we must then compare the speed of the baseball to the speed of the medicine ball for each of the different cases. Okay, so the first case, they tell us that the speed of the medicine ball is the same as the speed of the baseball. So this is a relatively simple case for us to analyze. The second case, they say that both balls have the same momentum. So as I've written here, the momentum of the baseball is the same as the momentum of the medicine ball. But remember, what we want to do is we want to compare the speed of the medicine ball to the speed of the baseball for each of the cases. So in order for us to make that comparison, it means what we need to do is substitute the values in, and then we need to rearrange the equation such that on the one side of the equation we have the speed of the medicine ball, and on the other side we have the speed of the baseball, along with some other numbers in front of it. So substituting those values in then and rearranging, we can see that the speed of the medicine ball is 1/10 that of the baseball. Here I've used the fact that the ratio of their masses is 1:10. Similarly, looking at case C, we told the kinetic energy of the two are the same. Remember, the symbol that we use for kinetic energy is capital K, and kinetic energy is given by half mv squared. Once again, we substitute the values in, and what we're trying to do is get the velocity, the speed of the medicine ball on the one side and the speed of the baseball on the other side. And in this formulation, you can see it works out to be that the factor difference between the two is the square root of 1/10, which is 0.31. So that means that the velocity of the medicine ball is going to be around about 1/3 that of the baseball. For the medicine ball, then, we asked to rank the different cases from easiest to catch to most difficult to catch. Well, we know the medicine ball will be easier to catch when its speed is low, and it will be harder to catch when it's moving with high speed. So what we effectively being asked is to rank the different cases from the cases of the speed of the medicine ball being low to the speed of the medicine ball being high. And if we look at the speed of the medicine ball for each of the cases, we can see that the slowest the medicine ball travels is 1/10 that of the baseball. The second slowest is case C, where it's traveling around 1/3 of the speed of the baseball, and the fastest the medicine ball travels is for case A, where it travels the same speed as the baseball. So ranking the order of the medicine ball from easiest to hardest to catch will be B, C, A. Something we're all familiar with in terms of wisdom in traveling in our vehicles on roads is the fact that speed can kill, speed kills. But it's interesting for us to think about it from a physics point of view in terms of what would cause more damage in a collision. Would it be an insect traveling at 60 kilometers per hour, or a bowling ball traveling with the same speed, 60 kilometers per hour? Well, you can think that you would much prefer to have an insect fly into you at that speed than to have a bowling ball hit you traveling at the same speed. And the reason for this is that what actually does the damage is the combination of the mass and the speed. So if you think about kinetic energy is half mv squared. So if you have a high mass along with a high speed, then it's far more dangerous than a small mass with a small speed. Although the fact that the kinetic energy scales according to v squared and not linearly with v means that the impact of high speed is in fact very, very dangerous. One of the learning objectives in the beginning was to rewrite force in terms of momentum, and this is what we do now. You'll remember that momentum is defined as mass times velocity. Then we know from Newton's second law, the sum of the forces is the mass times acceleration. So if you compare these two equations, you can see we already have a mass here and we have a mass here. But over here we have a velocity, right? And here we have an acceleration. So it would be a good thing for us to rewrite this acceleration in terms of a velocity. And you simply by definition, acceleration is the change in velocity with time. the mass is a constant, it's not going to change, so you can take this into the derivative, and then we get is equal to dmv over dt. Here you can see this term here, the mass times velocity, that's in fact the momentum. So the expression that we left with then is that the sum of the forces is the change in the momentum, which with respect to time. So this is a reformulation of Newton's second law in terms of momentum. If we continue on to look at the case of an isolated system, then for an isolated system we mean the sum of the forces is zero. So there are no external forces operating. So if we have the sum of the forces is equal to zero, then we have the change in momentum with time is equal to zero. Rewriting the derivative notation in terms of delta notation, the consequence of this is that the change in momentum must be zero. So this, from there it follows that we have that the final momentum is equal to the initial momentum, which is of course a conservation statement. So this brings us to the conclusion then, for an isolated system, the final momentum is equal to the initial momentum, and we have conservation of momentum. From this we go on to arrive at a definition for impulse. So we start with the formulation of Newton's second law in terms of momentum, which you've just seen. Multiplying both sides of the equation by dt, we arrive at the second line. We go on then to integrate the momentum from the initial momentum to the final momentum. So we integrate both sides. We also integrate the force over the time period from 0 to t. Remember, over here we have 1. There's a 1 written there. So if you integrate the left hand side, you can check it yourself. You get the final momentum minus the initial momentum is equal to this integral on the right side. We can't always explicitly go on to evaluate this integral because we might have a force that varies with time. And then from this we define the impulse to be this term here. Impulse, written as capital I, a vector, is equal to integral of f dt from 0 to t. Impulse gives an indication of the magnitude and the duration of the application of a force. So it tells you, it's an indication of how big the force is, represented by this term capital F, along with wrapped into it an indication of how long the force acts for. This will be given by the duration or the contribution of dt. To calculate the impulse, then we use this equation here, where the impulse is the change in the momentum. For a short period of time, we can also make use of this equation. The average impulse is equal to the average force over delta t, where delta t will be a small value for a short time interval. This f average delta t, this is actually a reformulation of the integral, which applies over a short time. Calculating the average impulse is useful when one force is much greater than others, for example in a collision. And if we have a multiple particle system, then we still have the conservation of momentum law that applies, except for multiple particle system, what we need to do is sum the momentum of each of the individual particles. Let's have a look then at an example of a problem involving the calculation of impulse. A car with mass 1,700 kgs moving at 13.6 meters per second collides with the wall. The duration of the collision was 1.2 seconds and the car rebounds with a velocity of 1.3 meters per second. Calculate the impulse and the average force exerted by the car on the wall during the collision. So what I've done here is I've represented all the information. We have, the initial speed of the car is given as 13.6 meters per second, but it's very important. We're going to be working with impulse and momentum, and these are vector quantities. So what we need to do is we need to take the direction into account as well. So I've taken, as per our normal convention, moving to the right will be the positive I hat direction. So the initial velocity of the car is this 13.6 meters per second in the I hat direction. It collides with the wall and then it rebounds or it bounces back with the speed of 1.3 meters per second. In this case, when it bounces off the wall, it's going to be, moving in the opposite direction. So it's 1.3 meters per second in the negative I hat direction. We're given the duration or the time in which the car is in contact with the wall when it makes contact with the wall. That lasts for 0.12 seconds. The first thing we asked to calculate impulse, and of course we should remember that impulse is a vector, so this should be a vector, right? Impulse by definition is the change in momentum, and we have the mass, we have the velocities, but this is at the step you need to just be really careful and to include the sign for the velocity. So VF will be minus 1.3 minus, VI is 13.6 meters per second plus 13.6 meters per second, and coming out to a final answer as shown here. Note that it's a negative value, and the interpretation of that is that the impulse is acting in the minus I hat direction. We also asked to calculate the average force exerted by the wall on the car during the collision. So we do that in the second part of the calculation. Here we use this approximation where the average force is equal to the change in momentum over time, and we saw the change in momentum, which is the same as the impulse. We have a value for that, remembering to include the negative sign. We know that the time is 0.12 seconds, and this then allows us to calculate the average force acting on the car as 2.11 times 10 to the 5 Newton. Of course, the force of the wall on the car will be in the minus I hat direction. Right, so now we take a look at an example involving the conservation of momentum. A burst of bullets, each with mass 40 grams, is fired horizontally with a velocity of 1000 meters per second and hits a 10 kg wooden block on a smooth table. What is the velocity of the block after 15 bullets are fired and remain stuck in the block? So this then's the situation that we have. We have 15 bullets being fired into a block. You'll note in my solution I'm representing the bullets by small b and the block by cap B in the subscript notation. So the mass of each of the bullets is 40 grams. So we need to take care to rewrite this in SI units. So it's 40 times 10 to the minus 3 kilograms. The initial speed of the bullets, V small bi, is equal 1000 meters per second, and the mass of the block is given as 10 kgs. This is the initial case. In the final case, we have the block and the bullets move together. So here we have the bullets embedded in the block, and we asked to calculate the velocity of the system. So this, I'm representing this as 0. So through the conservation of momentum, we have the momentum of the bullets plus the momentum of the block, referring to this, the initial momentum, is equal to the momentum of the final system. If we look at this here, you can see there are going to be 15 bullets. So this is where that 15 comes from. The initial velocity of the block is 0, right? Because to start off with, the block is at rest. So this whole term here is going to fall away. in this system for which we asked to calculate the final velocity, the bullets are now stuck within the block. So we have one whole, one whole block with bullets moving together. So for this, and they're both going to be moving with velocity v. So for this reason, we need to represent the combined mass as the mass of the block plus the mass of 15 bullets. What we asked to do is calculate v, the velocity of the system. So we simply make this v the subject of the formula, and we arrive at this expression here. Each of these quantities, the mass of the bullet, the mass of the block, the initial velocity of the bullets, these quantities are all known. So we can substitute the values in, and the speed we come to then is 56.6 meters per second. So we're going to conclude this chapter by looking at collisions. If we think of everyday, day-to-day life, and we think of the term collisions, then one of the most popular things we might think of is, a collision between two cars, a car accident. But in terms of our scientific description of a collision, the term collision represents an event during which two particles come close to each other and interact by means of forces. So here we have two different examples. In the first case, we have two masses, mass m1 and mass m2, and these two are actually, smashing together and colliding and exerting forces on each other as shown. In the second case, we have two charged particles. You can see this first particle has charge of +1, the second particle has charge of +2, and these two particles, they're moving close to one another, and because they're close to one another, they're exerting electrostatic force on each other. It's a force of repulsion, and they're going to change their trajectories. So it's interesting. In terms of the second case, we also term this as a collision. Even though the two particles don't come into contact, we still consider this a collision because the two particles have come close to each other and they interact by means of forces. The second point, the interaction forces are assumed to be much greater than any external forces present, so we can use the impulse approximation. So the meaning of this, the interaction forces are assumed to be much greater than any external forces present. You can imagine if there's a car accident with one car colliding into another car, then the biggest forces that are coming about as a result of this collision is the force of the two cars, on one another. The other forces, other external forces such as gravity and any other forces that might be present, those are almost secondary. We distinguish between two types of collision. The first kind of collision is elastic collision. The second kind of collision is inelastic collision. For both types of collision, we have momentum is conserved. So momentum is conserved in both cases. When we speak about elastic collision, we also have the conservation of kinetic energy. So for elastic collision, we have both the momentum is conserved and the kinetic energy is conserved. When it comes to inelastic collision, we have conservation of momentum, but the kinetic energy is not conserved. So the final kinetic energy is not equal to the initial kinetic energy. The reason why this isn't true is that some kinetic energy will be converted into different types of energy, such as perhaps sound, perhaps heat, perhaps energy to deform material, such as when cars get smashed together, some of the energy will be used to bend the material. So we'll have the fact that kinetic energy isn't conserved. A good example of an elastic collision is the classical example that's often given is that of two snooker balls or pool balls colliding. When it comes to inelastic collision, we also have a type of inelastic collision called a perfect inelastic collision. And for a perfect inelastic collision, this is one defined as a collision in which objects stick together after the collision. In this case, kinetic energy must be lost, or else it would have been an elastic collision. So in this course, we're mainly dealing with linear momentum and collisions in one dimension, but it's possible to apply everything that we've learned in two dimensions. For example, in this problem shown here, we have two perhaps pool balls, two snooker balls colliding and heading off in different directions. You can see this problem would relate to two-dimension problems. We have an x direction and a y direction. So we could equally well apply the concepts that we've learned here, but we would just apply them in each of the x direction and each of the y direction. And here you can see a formulation of the conservation of momentum in the x direction and in the y direction independently. Similarly, we could consider the collisions to be occurring in three dimensions, and we would have x, y, z, right? But anyway, this brings this chapter on linear momentum and collisions to an end. I encourage you to ask any questions that you have, or make any comments you would like to in the comment section below. Take care until next time.